We've now graphed sine, cosine, and tangent. The remaining trig functions we need to graph are the reciprocals of these three. So first, let's see what happens with numbers when you compute their reciprocals, and then we'll apply this concept to each of the graphs we've done. Talking about just positive numbers for the moment, the only number that is its own reciprocal is 1. When you take the reciprocal of numbers larger than 1, the result is smaller. 2 becomes a half, 4 becomes a fourth, and so on. These relationships work back and forth. If you take a number smaller than 1, its reciprocal will be larger than 1. In fact, the smaller the number you choose, the larger its reciprocal becomes. Let's see what these relationships look like visually. We'll draw a line at 1, since that number is kind of the dividing line. Think of this line as a special sort of stretching mirror, where if you look into it, you see your reciprocal. A point right on the mirror will stay there. In mathematics parlance, we call that a fixed point. If we move away from the mirror to lower numbers, at first the mirror seems to reflect at least kind of accurately. But as we continue to drift lower, the reciprocal moves much further. In fact, the closer we get to 0, the larger the reciprocal gets. Pairing numbers with their reciprocals matches up all the numbers between 0 and 1 to all the numbers larger than 1. In effect, if we send this short length of space through the mirror, it becomes infinitely long on the other side. When we look at reciprocal graphs, any portion between 0 and 1 will get stretched to the other side, and any portion above 1 will get compressed into that little span between 0 and 1. Negative numbers behave similarly, just in the downward direction on the graph. Of course, if we try to take the reciprocal of 0 itself, it becomes undefined, and that typically leads to an asymptote on a reciprocal graph. With those ideas in mind, let's start with the graph of secant, which is the reciprocal of cosine. Here is the cosine curve. We're going to send the positive portions through our special reciprocal mirror that's at y equal 1, and the negative portions go through the mirror that's at y equal negative 1. Any points at those y values, 1 and negative 1, will remain where they are, so let's mark those. Any y values of 0, namely the x-intercepts, will correspond to vertical asymptotes on the secant graph. We'll indicate those with dashed lines. Let's send just the positive middle part through the mirror first. Remember that the closer a point is to 0, the farther away the reciprocal will be. This resulting U-shape, for lack of a better term, is infinitely tall. It stays in its lane between those two asymptotes and gets increasingly closer to them, but never quite reaches them. The same kind of result happens with the negative portions too. They just head downward. We now have one complete period of secant with length 2 pi. Note that the period consists of 2 of those U-shapes, one up and one down. It's okay that there's a gap between them. If we push the rest of the cosine wave through the mirrors, we get repeated copies of those U-shapes. It's certainly a strange-looking graph. One thing to notice, the cosine function had output values from negative 1 to 1. Those are precisely the numbers that secant doesn't include. Well, except for 1 and negative 1 themselves. Here's one way to draw secant by hand. Lightly draw the cosine curve, draw vertical asymptotes at its x-intercepts, and then draw the U-shapes between the asymptotes so that they just bump up against the high and low spots of the cosine wave. And then erase the cosine graph. Cosecant is very similar to secant. We just draw the reciprocal graph of sine rather than cosine. So we'll start with the sine curve and then send it through our special reciprocal mirrors. The result has the same shape as secant, but it's horizontally shifted, just as sine and cosine are horizontally shifted copies of each other. Notice that the vertical asymptotes shift as well. Here the asymptotes are located at 0, pi, 2 pi, etc. For secant, the asymptotes were at pi over 2, 3 pi over 2, 5 pi over 2, and so on. Finally, to graph cotangent, we need to find the reciprocal graph of tangent. This one will feel a little different because each period of tangent is infinitely tall, so our special mirrors are going to create another shape infinitely tall. Here is our graph of tangent. As we did before, let's mark any points that are a y value of 1 or negative 1. Those points will remain seated. Then the x-intercepts of tangent will correspond to vertical asymptotes of cotangent. Let's draw those in. Look at just the positive portion of the center shape. The part with y values between 0 and 1 is going to get stretched to the entire space from 1 to infinity. And then the portion of tangent from 1 to infinity will get compressed down to that little 0 to 1 space. We get a similar result with the negative portion of the curve. Amazingly, the resulting shape is identical to the shape of tangent. It's just inverted. Let's send the rest of the tangent graph through the mirrors. Not only are the resulting shapes inverted versions of the tangent curves, they are also shifted horizontally. Notice that while x-intercepts of tangent became the asymptotes of cotangent, the reverse happened as well. The asymptotes of tangent became the x-intercepts of cotangent.